And then go to the next major topic. Is cavity. Now, it's similar to waveguide, but it's just cut off. Basically, a waveguide for us is the rectangular waveguide. Obviously, a cavity can be arbitrary shape, can have cut, but the only thing we actually can calculate it easily is more regular shape. So we start with the rectangular waveguide with invariant direction along Z. Basically, the cross section is the same everywhere. Now we cut off the two cross section at Z equals to 0 and Z equals to, I think it's D. Is it D? Yeah, D. And then for the basic case, set all the surfaces as perfect conductors. The sigma is infinity on all surfaces. Okay, so we get all these ideal mode. All right. Now the consequence of this.
If we remove portion from
so of course outside it doesn't matter. After you cut it off, you only consider interior. You consider the E and B. Okay, inside the cavity, obviously you still assume it has the mu and epsilon. So a certain kind of medium inside. Okay, outside is just perfect conductor. You don't. That's not what we will consider outside, but inside want to calculate the wave mode of this electromagnetic field. Okay, so with this boundary, the first thing you change is that now the wave is no longer just propagating in one single direction. With a waveguide, the wave can propagate either positive or negative Z direction, and we represent that by either the IKZ or plus or minus IKZ, whether you take K as with sign or not. Right. But for a cavity with both end, you basically restricted with a finite volume. So you cannot have just a single direction wave because you propagate in one direction, it will reflect back and so on. So this will have a standing wave. And what we want to look for is some kind of steady state, or what we call the eigenmode. And that means that if you have an eigenmode, we stay there, just the single figure is just oscillate back and forth. With perfect conductor, meaning no dissipation, it will just go on forever. That's the eigenmode. And so these are called, the frequency of these eigenmodes are called resonant frequency. Right? You want to find those frequencies, obviously also the wave structure within the cavity. So that's the key. But one property is obviously they are standing waves. So along Z direction, instead of E to the IKZ, now we change to a standing wave. And to represent standing wave, we can either use cosine KZ or sine KZ, or combination of both. Right? Because both sine and cosine are a combination of e to the IKZ and e to the minus IKZ. So we could propagate both ways. It's easier to use this than this one, than what we did before. Because what we did, if you use this one, we need to include two terms, and that make all the equation complicated. Okay, so we start with that. And the second step is the same now. To consider either the TM mode or TE mode, right? So that is fine. But then for TM mode and TE mode, the boundary condition will be different. The boundary condition on the side will be the same, but the boundary condition on these two new boundary at C equals 0 and C equals D would be different. Right? Different from the waveguide. The side surface, the side, so for like, which actually for this case, for the end surfaces, TEMO turns out to be easier. The TEMO side is the parallel direction of the magnetic field. You can use either HC or VC. Let me see. Just use H, right? Just use H. So psi will be proportional to. We'll choose the proportionality constant either on either side. But we will then impose the boundary condition first. Consider boundary condition first because it's proportional to the magnetic field and along the z direction. So it means you have a magnetic field z component on both surfaces. And if you go back to the first section, you know that for perfect conductor, Hn is 0. You can go back to H. This is Hn. It's actually H. Just use the term that perpendicular, H perpendicular. Perpendicular in figure 8.1, perpendicular means perpendicular to the surface, which is this direction. Because the HC is H perpendicular on the surface, so that is 0. So I can say psi at C equals to CD is 0. By the fact that HC is H perpendicular on the surface. So, so that is quite easy for TEMO. You just set this to 0. And we have done this before. You have a surface. I mean, you have a wave quantity that at C equals 0 and C equals D is 0. So obviously, a function that will make it so is the sign. Actually, right, the other way around. So what we'll impose is, because HC is equal to psi, which depends on X and Y, or the cross section, and then sine. Let me just use the P. Let's use P. P I C over D. And in this case, obviously, P start from 1 because if it's 0, then the whole thing is 0. That becomes no mode. All right, so that would be just the wave structure of the TEMO. Now this psi, we solve psi by the same wave equation, perpendicular wave equation. That we know that perpendicular wave equation is Laplacian plus gamma squared. It's subject to the boundary condition. And for this, obviously, this already satisfies the boundary condition at both ends. So the boundary condition for the TEMO is still partial psi, partial n. On the side surface is 0. Okay. That's still true. That's TEMO. Oh, okay. For TMO, psi is proportional EZ. Now to determine the boundary condition is slightly more complicated. We need to go back to a few equations to look at the boundary condition. Let me look for it. We got Jackson did. I was looking at Jackson whether he pointed out where the boundary condition is. No, let's just go back to those equations that we did. So this is TE. So you can go back to equation 8.23 to 25 to see which one we can use. So easy is psi. You can use maybe the first equation, 8.25. Let's see if this is, we can use that. We need a partial part. So you change the order, become partial EZ, partial C equals to minus transverse divergence of ET. Okay. ET is transverse electric field. Transverse electric field on these surfaces, on the end surface. So this is E parallel according to 8.1, the figure 8.1. Great. Figure 8.1, at the boundary, at the surface, E parallel is 0, but this all the ET on the surface is 0. ET on the surface is 0, and therefore the gradient of transverse divergence of ET is also 0, because transverse divergence only involve derivative along the surface, but along the surface the whole thing is 0, right? So this must be 0. The partial EZ partial Z is 0. So EZ is proportional to psi. So what we want to impose is partial psi, partial C at C from at 0 or D equals 0. Right? That is what we want to impose. And now we know that something similar to here, the partial psi, partial C will be 0 if partial psi, partial C on the surface is given by something like sine p pi z over d. But this is a derivative, so basically you're integrating that. So one thing to impose this is set EZ equals to psi x and y. Now you multiply by cosine p pi z over d. Right? Because now you take the derivative, partial psi, partial c, that will change the sign, multiplied by pi, p pi over d, and negative sign. But this will be 0 at both c equals 0 and c equals b. Okay, so that will work. And for the TM mode, the surface, side surface boundary condition is psi s is 0. It's still true. This is a function of x and y only. The z dependent is also all in the cosine. So the side surface boundary condition is you set this to 0, which is the same as the waveguide. All right. So we already set up the how you solve for the wave mode for the cavity. Okay, so what we need to do is eventually solve for this one. And gamma square, let's see, gamma square is omega square mu epsilon minus k square, and in our case, k is just p pi over d for both cases, right? Because this is cosine kz, this is a p pi c over d, so k square is just p pi over d. We haven't set the limit of p, but this one, this is a cosine, so it allowed p to be 0. So p can be 0. 1, 2, 3. When p equals 0, obviously this is just 1. So easy is just psi times xy, because but it's still non-zero. So this is allowed p equals 0. Okay, and now this is gamma, but when we solve this wave equation subject to this the cross-section area, I mean over the cross-section area subject to these boundary conditions for the TE and TMO, and the usual case is that the gamma squared are discrete eigenvalues. They are the gamma squared depends on what the mole is has some discrete value. We indicate that by lambda, which is one of the eigenvalue. So by this one, then you can solve for the resonant frequency. So you can indicate that by omega lambda. This is different from the cutoff frequency that we talked about. I mean, it's slightly similar, but it's not exactly the same. So now it's equals to this wonderful mu lambda square plus okay, so that's the formula for the Western frequency. So once you solve for gamma, then you use that to get all the Western frequency. Is that okay? No.